Yo, 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 what is up, AS Math? It is your host with the most, Mr. Knight. I apologize in advance for that intro. We are continuing on with vectors and working with vectors, and today we're going to look at vector calculations. So adding and subtracting them, multiplying them by stuff, a lot of different things that we can do with vectors. And again, I'm throwing a lot at you, but these are a lot of little micro skills that we're going to need to be successful for this unit. So first things first, multiplying a vector by a scalar. Remember, a scalar is just some kind of value. It doesn't have a direction associated with it. And so what I'm going to do is, or what I did rather, was I have these two vectors right here. So vector A, I'm just going to call it in component form. It's going to be equal to this stuff right here, and we're going to pretend it's in 3D. And then this vector, it's going to be the A vector, but it's double the length, so double the magnitude of this guy. So mathematically, to see that, essentially what we are doing, and I'm going to show it in two ways, is we're taking the scalar, which is our 2 in this case, and what we're going to do is we are going to distribute it to this vector in component form. So if you distribute it, you end up just getting 6i minus 10j plus 2k. I also went ahead, I wrote the vector out the other way, kind of in this form where you have x, y, and z like this. These are your components, and so you can do 2 times this, and you will end up getting the same exact thing, regardless how you do it, okay? And that's just multiplying by a scalar. It's just distribution of that number. The negative of a vector. Again, it's basically just like multiplying a vector by a scalar, except that scalar is going to be -1 now. And so if I have some kind of vector A, and now I take the negative of it, well, that is the negative of this whole thing, so I have to distribute the negative to every component that's in here. And so this would be my negative A vector right here. Okay, not too bad, not too bad. And of course, there's a consequence to having the negative of a vector. If I have vector A going this way, I take the negative, well, I end up having to flip the direction of my vector. Okay, the vectors go in the opposite direction when they are negative. Okay, so adding and subtracting vectors. Let's see how this guy works out, because you really just got to see how it works out. If I have vector A, then that's equal to 2i minus 3j, and I have vector B, who has its own set of components, then if I wanted to do the vector of A plus vector B, well, I just combine like terms, but I'm calling them like components, you know. So the i's are going to add together, the j's are also going to add together, and so what I did was I lumped the i's and the j's together, and you could see that right there in the green, and so we end up just getting A plus B vectors equals 5i plus 2j, and that's it. But to see that a little bit graphically with the actual vectors, let's kind of see how to add vectors if we're not doing it algebraically. Okay, I guess that's not really algebraically. Yeah, it's algebraically. It's something. So here's vector addition. I know this looks really, really wild, so I color-coded it to hopefully help that a little bit. Okay, so in the last problem, we just had vector A and B. So we're going to focus on the green and the blue right now. Well, if I want to get my vector A, well, I know the component is 2i, so I go 2 in the x direction and then -3 in the y direction. And so my vector is going to end up going down like this, and that's where I end up. With vector B, what I'm going to do is from this point right here, and really, these vectors are out in space. They're kind of just random. So I could have put this guy right here, starting at the origin, but I didn't. Okay, you're going to see why in a little bit too. But again, to get this guy, I go over 3 in the x direction. Now I'm going to go up 5, so then I land right here. Okay? And so my resultant, and that's actually what we call this guy, the resultant is the vector we get from adding our vectors together. And so that resultant vector is going to start at the tail of vector A, and it's going to end at the tip of vector B. Okay? So let's kind of formalize that a little bit. So the sum of two or more vectors is the resultant, this R vector. And to add vectors graphically, we actually go tip to tail, right? So we go tip to tail. So I start from this tail from the origin, and then my next one, my B, what I'm adding, is going to start from this tip and end up here. And so this is kind of how it would look if I just took the coordinate plane off, which I think is a little bit easier to see. So let's pretend this R isn't here for right now. So we're going to end up having this A vector, then we're going to have the B vector. I threw in an extra C vector that we could just be adding, so this is really just A plus B plus C. And so what ends up happening is, to get the resultant, I need to go from the tail of the first vector, right here, and I need to go to the tip of the last vector, which is C, okay? So that's kind of how you add these guys up. You go from here to here, and then the next one is going to continue, then the next one's going to continue. The resultant is, well, tail of the first vector, tip of the last vector. Why is this important? With these guys, we're going to see when we get into more geometric figures working with vectors that this might come in handy when kind of figuring out how vectors are oriented in space. And so it will be of use to us. Subtracting vectors. Subtracting vectors is the same as adding the negative, okay? So if I have these two vectors and I want to do the subtraction of it, well, that is the same thing as just doing A plus the negative of B. And really what you can do is, so you'll take this first vector, the 2i plus 3j, minus whatever your B is. And so, again, I'm just going to distribute this negative to my components in here. So I end up with this guy right here, the signs changed, and then I combine my like components, and so I get 3i plus j. That is the answer of A vector minus B vector. Okay? We're rolling, we're cruising, I'm throwing a lot at you. Next thing, unit vectors. We have briefly mentioned these. We kind of gave a definition of what it is. Vectors of magnitude, vectors with a magnitude of 1, that's what we refer to as unit vectors. And these vectors are always in the direction of the vector that we're trying to, well, get the unit vector of, right? So we'll have some vector A, and unit vector is represented by A hat, because it has a little hat on it. And so the equation to get the unit vector, and we're going to do an example of this, is my unit vector is equal to 1 over the magnitude of my A vector times the A vector itself. It's kind of weird. Let's see an example of that so that kind of makes sense. So I want us to find the unit vector of this C vector right here. Well, the first thing I'm going to do, if I'm using that formula, well, I got to find the magnitude of this guy. So the magnitude of this is taking all the components, the 6, negative 5, the 1, squaring them all, taking the square root of that. So basically like a little bit more of Pythagorean's theorem, but in 3D. And we're going to get the square root of 62 equals the magnitude of our C vector. Now, what I would do, I would keep it as a square root. Okay, this makes it a little bit easier. You don't have to worry about a decimal. Okay, so now what I'm going to do is C hat is going to equal 1 over my magnitude, which is square root of 62. And I'm going to basically distribute this guy to each thing of my C vector. And so all I'm going to get is 6 over the square root of 62, and really all of my components are going to be over the square root of 62, which looks absolutely disgusting. And that's kind of my fault because I made up this problem on my own, but the process is still the same, and you're going to get these as unit vectors. And again, these are just the components. So if I were to add them all up, which who would do that? That's crazy. But if we did, we added 6 square root of 62 plus negative 5 square root of 62 plus, and we squared all those up, took the square root, our magnitude for this guy would end up coming out to 1. Okay. But for right now, I would like you to just try on your own to find the unit vector b given this b vector. Give it a shot, and let's see what you come up with. And we're back. Let's see how we do this. Well, we have this b vector right here. The magnitude is going to be the component squared added together. I take the square root of that. I end up getting square root of 9, which is just 3. So my unit vector b is 1 over 3 times, well, the 2 over negative 2, negative 1. And so it's just 1/3 times all these. And so my unit vector b should equal this guy right here. Okay? And again, their magnitude should equal 1. So if you wanted to check, you could add all these up, square them, take the square root, and you should get a magnitude of 1. Okay, now here is probably the most important part of this lesson, I'd say, is vectors from position vectors. So, I kind of messed up a little bit, so let's take a look. Let's see what happened. If I have this line segment PQ, I can actually find the vector PQ by actually using my slope formula. Because if I think about it, I just need to think, all right, what is my x direction for my x component? What's my y direction for my y component? And so I can do that by just finding my rise over run. So I went ahead and did that. Well, here's my rise over run that I get. I get 4 over 1. But when we write that, and I actually made the mistake, we have to write it as x and then y when we write it in parentheses like this. And I'll pull that out so that looks a little bit more clear. PQ is equal to 1, 4, like this. Okay? And so, how exactly are the vectors coming into play? And more specifically, how are the position vectors coming into play? Because we didn't even use them. Well, let's see. You don't have to write all of this down. I just want you to see it for right now. I will tell you what is important to write. Okay? So points P and Q, we can actually represent them as vectors using position vectors because before they were just points on this graph and we found the vector from P to Q. But what if I just want the vector P and the vector Q? Well, typically the position vectors is what we use. And remember, position vectors are vectors that start at the origin. So both this P vector and Q vector are starting here. And so what I can do is I can represent this as the Q vector is equal to the point O, or origin, to point Q. And that's going to equal, well, my x component is 3, my y component is 5, and it's really just the coordinates of that. That's how it worked out, right? Same thing with vector P. I'm going from O to P. Now, somehow from these position vectors, I am somehow getting PQ, the vector PQ represented in this red, represented as this red, I'm somehow getting that to be 1 over 4. And we saw that with slope, so it does make sense. But let's go ahead and see what's going on. So to get PQ, I can actually subtract OP vector from the OQ vector. And so I'm going to actually use Q and P instead. So we call I'm subtracting OP from OQ, so starting with OQ, that's my Q vector, minus my PQ vector, which was P. And we saw that those would equal 3 over 5 minus 2 over 1. And again, if I just do my vector subtraction, I end up getting 1 over 4 for PQ. And this actually reveals something a little interesting to us because we found this PQ vector right here, okay? And so you can actually see that graphically how we did that. If I'm starting from vector Q and then I subtract vector P, so I have to take the negative P and add it to it. So now that vector is going the other way. Sorry, I can't do it with my hands. It's going this way. And then the resultant is from this starting tip or starting tail to the tip of the final one. So it actually ends up looking like that vector. But the interesting reveal is that the vector of a line segment, if I have something that's PQ, that's the same thing as Q vector minus P vector, where those vectors are position vectors. They are starting from the origin and ending at point P or point Q, similar to what we saw right here. Okay, so anytime you have a vector that you're trying to find or you're trying to calculate, it's just going to be this position vector minus this position vector. Okay, and it's going to be actually pretty powerful. Okay, and we're going to use some of these ideas of adding vectors and position vectors to kind of help us out with this class example. So I totally 100% drew this, as you can tell by the tape. Maybe you can't. Oh, you can't even see the tape. Cool. There's no tape. I lied. Here is an example of a hexagonal prism. Okay, what we're going to do is we have these vectors P, Q, and R, and we're going to actually represent a lot of these like BC vectors and the AB vectors. We're going to represent them using P, Q, and R. Okay, so we have this hexagonal cross section. It's regular, so what that means is that the AD vector, so basically if we had a vector from A to D, is going to be 2 times the length of BC. Okay, that might be important to know. We also know that vector AB is the same as vector P, and likewise for BC it's Q, BG it's R. So let's express the following, we have 6 of these guys, in terms of P, Q, and R. So let's start with AC. If I start with AC, well, that is a vector that somehow has to go from here to here. Okay, so using my pen as kind of the vector, it's going to look something like that. So to get there, let's think about how we add vectors. And I did it right here, but I want you to see it graphically. We are going from the AB vector, and I'm adding that, right, because I'm adding the tail of BC. I'm adding that on to the AB. So I go AB and then my BC. So AB vector plus BC vector equals my AC vector. That would be the resultant right there. So I can write that as AC vector equals those guys. And I know what those are in terms of P, Q, and R. It's AB is P, and then Q represents BC. And that's it. That's all I had to do for that guy. So let's run with that idea a little bit more. Let's look at AD and see what we have to do for that one. I'll keep this handy so we can refer to it. Okay. So for AD, we know that AD is actually equal to 2 times BC. How do we know that? How do we know that? Well, it said in the problem that AD was double this guy right here. So that's actually really nice to know. And I know what BC is. BC is, well, the Q vector. So I can change my BC vector. Since it equals Q from the last problem, I know that AD vector is going to equal 2Q. Okay? Now, the last one that we're going to do together, before I let you try some, is we need to figure out what HI vector is. Okay? We need to figure out what this HI here is. Well, that's kind of crazy. But we do know that HI and CD, they've got to be congruent. They're the same size. They would be the same vector if I had them. Okay? And it is HI equal to CD and not DC. Because if it's DC, well, our vector would be going that way, and that would be the negative of this. So it's important we're going HI. Yeah, we need something that has CD in it. We need some kind of relation. Well, we know from the last problem, and really we can also kind of look at this too. We know that if I wanted to have CD, at least CD included, I know that AD, this vector, is really equal to AC plus CD. That'll help me get to AD. That'll be the resultant. Okay? The reason I'm using those ones is because I know what AC is now because we found it earlier. We also know what AD is because we found that guy earlier. So now it's a matter of just finding CD, and if I know what CD is, I know what HI is. So CD is going to be equal to, I'm going to move all this stuff over, and so what we end up getting is CD is equal to vector Q minus vector P, and so HI has to equal the same exact thing. Okay? And so what I'd like you guys to try in class, I'd like you to try parts 4 and part 6 on your own, and go ahead and struggle with it, and ask for help, but try to work together on it and see if you guys can come up with it. Go. All right, we're back. Let's see. So part 4, it's very subtle, But here's the trick. IJ is the same vector, so IJ is the same vector as DE, actually. It's just a 3D figure, so it doesn't look like it in a 2D space, but yeah, this guy is actually going in that same direction. So if I know that, I know that's also the same as negative AB, because if this is DE going this way, well then going the opposite way, going BA, well that would be what negative AB is. So I know what AB is. AB is P, so the negative of that is just negative P. So IJ equals negative P. Okay. Part 5. Again, another trick. EF, that guy is going to be equal to negative BC. And so negative BC is this guy, BC is going this way. And so going EF, I have to be going the other way. So again, same idea. It's negative, and I know what that is. It was Q, so it's negative Q. All right. And then finally, part 6 for BE. Again, I want this guy. I want this resultant vector. So what I got to do is I got to go BC plus CD plus DE, and that'll get me to BE. And again, I know what all of those things are from previous problems. So I plug in these vectors that are alike, and so I end up getting 2Q minus 2P. All right, and that is our lesson.